Hello, my humans. Let's see what we are going to do here. Ooh, we're going to have some application problems. So we're not going to get too in-depth with these, but we're going to spend a little bit of time talking about what it means to make some use of some of this calculus. Later in the course, we'll have some more interesting questions because we can do a lot more once we actually know more calculus. But here it asks us, what does it mean to minimize, maximize material cost, or whatever? Well, so for example, if I think of water bottles, there have been some companies that have claimed that they have reduced the amount of plastic used in the bottle for environmental purposes. So they've tried to minimize the amount of plastic they've used, so the volume of plastic that they've used. They've totally done it for economic purposes to save them money, but they'll sell it as an environmental thing. It's like they made I don't know if you're aware of this, they made the tops of those plastic water bottles smaller. For environmental purposes, we should just eliminate plastic water bottles altogether because they're not actually good. But since we have them, companies have tried to do some stuff there. So to calculate the min-max stuff, that's where our calculus will come in. Because we've been talking about, if we have these curves, how do we find the max there? How do we find the min there? And we do that using calculus. So let's see what we got. So we've got 10-inch length of wire you wish to form into shapes. You determine how to cut the wire to minimize or maximize the area of the resulting shapes. Suppose you wish to make one cut in the wire and use the two pieces to form a square and a circle. Determine how to cut the wire so that the combined area enclosed is as small as possible and as large as possible. So if we have a square, let's call it x by x, that's x squared. And if we have a circle, let's call it the radius r, that's pi r squared, and that's your total area. In order to minimize or maximize that, we'll have to take a derivative. But let's see, do we have another equation we can write? We know we have 10 inches of wire. So doesn't that mean that 4x plus 2 pi r is equal to 10? And I'm trying to decide what is easiest. I guess I'll get rid of x. So I will solve for x. So 10 minus 2 pi r over 4. And then I'll plug that in. So 10 minus 2 pi r over 4 squared plus pi r squared equals the area. So to find min-max stuff, we want to find a derivative. So our derivative in this case is known as dA dr. So I'll do chain rule. 2, leave the inside alone. To the first, multiply by the derivative of the inside. 10 goes away. Negative 2 pi over 4, because that's the derivative of that second piece. And then 2 pi r. And we want to find out where that is equal to 0. So this is pi over 2. This is pi over 2 over here. Multiply that by 2, so it's just pi. And now that we have the pi, let me switch colors on you. We're going to cross the 2 out. So distribute that. So that's negative 10 over 4 is 5 pi over 2. Distribute the negative to there. That'll be plus 2 pi squared r over 4 plus 2 pi r equals 0. Let us go ahead and, through the magic of algebra, add the 5 pi over 2 over and then divide by pi squared over 2 plus 2 pi, which I guess if you wanted to, you could get rid of pi's from everyone and multiply everyone by 2. So 5 over pi plus 4 So now we need to consider a dAdr number line. So we have dAdr, and we have 5 over pi plus 4. So, well, 0 is less than that. So if I plug 0 back in up here, this part's 0, so that doesn't matter. This part's 0, so that doesn't matter. That's 10/4, and that's a negative, so that would be a negative number. So we go negative to positive. So the minimum area when r equals 5 over pi plus 4. Then we just need to think about endpoints. And the endpoints are basically where we only have a square, so only square. And that means we have 2.5 and 2.5, so the area is 6.25, or only circle. And that's where 2 pi r is 10, so r is, what is that, 5 over pi? And pi times 5 over pi squared is about 7.96 and a bit. So that's the max. Now I didn't write this up kind of as organized as I would like, partially because I was struggling with the space I have. But the key here is I ultimately could write these two equations, one where I had all the information, well, one where I had two variables, the 4x plus the 2 pi r equals 10, one where I really had three variables, but then I used the two variable equation to plug it into the three variable equation to make my life easier. So that's an example of optimization. Your optimization problems from your book are going to be similar to that, and you just want to play with them and see what happens. And then we'll talk about it in class. Alright, so now we have implicit differentiation that we were calling. Find the derivative with respect to x, find the derivative with respect to t, find the derivative with respect to y. So a whole bunch of things. So let me shrink this, if it lets me, there we go. So with respect to x, so this is product rule. So the derivative of x squared is 2x, y plus x squared dy dx, minus the derivative of 3x is 3, y minus 3x dy dx, plus the derivative of y squared, which is 2y, chain rule, dy dx, equals 0. That's with respect to x. With respect to t, it would be 2x dx dt, y plus x squared dy dt, minus 3 dx dt, y minus 3x dy dt, plus 2y dy dt, there's a lot going on here, equals 0. And the last, if that one confuses you, make sure you ask about it. Try to process it yourself. With respect to y, so the x squared is still 2x, but that's dx dy, which is wacky. We haven't done that yet. With a y plus x squared, derivative of y is just 1. And then derivative of x is 1, but dx dy, minus 3x, derivative of y is 1, plus 2y equals 0. So play with those and see if you can understand what I'm doing, because I agree it's a little bit wacky there. Now we got Linda. Oh, these are my favorite. Linda is bored and decides to pour an entire container of salt into a pile on the kitchen floor. She pours cubic inches of salt per second. Sorry, I can't see that other side because there's a thing there. 3 cubic inches of salt per second into a conical pile, that's a cone, whose height is always 2/3 of the radius. So the height is always 2/3 of the radius. So in these cone questions, there's a similar triangle thing going on, which I can explain. So I guess I'll just do the first part. Y'all can figure out the rest. How fast is the radius of the conical salt pile changing when the radius of the pile is 2 inches? So we have a volume. So this is related rates. Sorry, let me get there first. I got too excited by the Linda being bored because there's another part where I think she's further bored and pouring sugar or something. But this is related rate, so this is different from optimization. Optimization deals with how to maximize and minimize stuff. Related rates is how fast things are changing in relation to one another. So the volume of a cone is the area of the base times the height divided by 3. So the area of the base is a circle times the height divided by 3. We learned that the height was always 2/3 of the radius. So that means the volume is pi r squared 2/3 r over 3, which using the magic of algebra is 2 pi r squared over 9. 2 pi r squared, by squared I mean cubed. Now I want to take the derivative, but I want to take the derivative with respect to time. That's a key part for related rates. dv dt. So that's going to be, the 2 pi over 9 is a constant, so I can just ignore that. It comes along for the ride. The derivative of r cubed is 3r squared, and then dr dt. So I'm asked how fast is the radius, so that's dr dt, when the radius is 2. We know dv dt, that's that 3. So that means we'll have, change colors again, 3 equals 2 pi over 9 times 3 times 2 squared dr dt. So let's do some magic here. That will cancel with that and leave me with a 3. That's going to move over there and be a 9. And then I'm going to have 8 pi. So 9 over 8 pi is my dr dt. That's a dr. I don't know what happened there, but that's an r. So related rates, you're taking the derivative with respect to time, and we're rolling from there. Oh, see, I told you, Linda's still bored. So this is the same idea. Keep playing with these and asking questions. It's still cones, so you can handle it.